Let's apply the Force Toolkit in some useful examples. So make sure to pause the video and write these steps down. The first thing you need to be able to do when you use the Force Toolkit is identify the system that is being accelerated. Then define the coordinate system. Identify the forces by drawing a force or free body diagram and include a motion map. If necessary, draw a component diagram, and if necessary, rotate the axes. Explicitly write the sum of the forces equals mass times acceleration. Replace the sum of the forces with the actual forces in your free body diagram, and if necessary, write the sum of the forces equals ma in the horizontal and vertical directions. Substitute numeric values where appropriate and solve for unknowns. So our first example is one in which you're in a grocery store and you push a 14.5 kilogram cart with a force of 12 newtons. If the cart starts from rest, how far does it move in 3 seconds? So the first thing we want to do is identify the system that's being accelerated. So the system that's being accelerated in this situation is the cart. Then we want to define the coordinate system. In our coordinate system, we want to say up is positive and to the right is positive. We want to identify the forces by drawing a force or free body diagram and include a motion map. So in this situation, our motion map is going to include the normal force, because the surface is pushing up onto the cart. Something's pushing the cart, we can call that the applied force. And then, obviously, the force due to gravity. We don't need to draw a component diagram, and we don't need to rotate the axes. We want to explicitly write out that the sum of the forces equals the mass times acceleration. Then we want to replace the sum of the forces with the actual forces in our free body diagram. So you'll notice that in the vertical, our forces are the normal force plus the force due to gravity equaling ma. But obviously the cart's not moving in the vertical, so there's nothing going on, so that will equal 0. In the horizontal, however, we're told that the object starts from rest and then is pushed to the right. So in the horizontal, we do have a force, but there's only one force, and it's this applied force. So we're going to, in the horizontal, write that the applied force is equal to the mass times acceleration. Then we want to substitute our numeric values where appropriate and solve for any unknowns. So in this case, it looks like our applied force is 12 newtons. Our mass is 14.5 kilograms. And our acceleration is unknown. So what we therefore do is divide both sides by 12 newtons, and we get 14.5 kilograms divided by 12 newtons. And we get an acceleration of 0.828 meters per second squared. Now to figure out how far it moves in 3 seconds, we therefore go to our strategy. So our strategy always starts off with x, v initial, v, a, and t. We know the acceleration because we just solved for that. That's 0.828 meters per second squared. It starts from rest, so our initial velocity is 0 meters per second. And we want to know how fast or how far it moves in 3 seconds. And because it's asking how far, our unknown is our displacement x. So our equation would be x is equal to x initial plus v initial t plus 1/2 at squared. This part goes to 0 because initial position is 0, initial velocity is 0. So we're just solving for x is equal to 1/2 at squared. We plug our values in. And we get a value of 3.73 meters. And to make sure we do this correctly, let's show our motion map. So the reason the motion map is helpful in this situation is it tells us what is actually happening. The object is going from rest, so we would start off with a dot for the velocity, and the velocity arrows increase towards the right. And so because the velocities are increasing, we remember that the acceleration must point in the same direction as the increasing velocity. So this is really helpful because it shows us that in the horizontal direction, that the net force, which is that force, is in the same direction as my acceleration. In the vertical, if we were to draw the motion map, we would just have a dot for velocity and a dot for acceleration. Because as we notice, the normal force and the force due to gravity cancel each other out.